Today in the workshop, we're taking another look at infrared remote controls. We'll examine the hardware and sketches used to encode and decode IR remote control signals, including those difficult devices like AC remotes. We'll also build an ESP32 based remote control with a web interface that you can customize for your own purposes. You'll find it more than remotely fascinating, so welcome to the workshop. Well, hello and welcome to the workshop, and today we're revisiting a subject that we looked at almost 5 years ago, infrared remote controls and microcontrollers. Now, you've probably got a house full of infrared remote controls. We use them for everything these days. Of course, they're used for televisions, but they can also be used for appliances like air conditioners and lamps. And by interfacing with a microcontroller, we really can open up a lot of possibilities. We could use a microcontroller to control these devices that are normally controlled by an IR remote, or we could use the IR remotes to control the microcontroller. We can also interpret the IR remote signals and change them to another manufacturer's IR remote signal if we want to, so that we can use one device with another manufacturer's controls. There's a lot of possibilities here. Now, this is a very long video. In fact, I had to cut it off because I have 3 more IR remote projects I wasn't able to present, but I am presenting one at the end of this video, and we'll look at the other 3 in another video. But today we're really going to get deeply into the subject. We're going to look at the hardware first, we're going to look at the emitter diodes, and also at the IR sensor, the TL1838 that you normally get in those kits from Amazon is a very old sensor, several decades old, and there are better ones that you can use with modern microcontrollers. We'll look at that. We'll look at the newer updated Arduino IRremote Library. That's what kind of broke the last video, because when they went to version 3, they changed the method of calling the library and all the old code broke. So we'll go through all the new code with that, and I'll also show you another library that understands a lot more remote controls. But if you've got one of those pesky remotes that none of the libraries install, I have an air conditioner remote that falls in that category, I've got a technique for you that will allow you to interpret those remote controls as well, and I'll be showing you that near the end of the video. And as I said, I've got a project for you. It's an ESP32 based remote control. It has a web interface. You can put as many buttons on it as you want and use your phone or your tablet as a remote. So it's pretty futuristic. But before we jump into that future, I thought it might be a nice idea to look back and see why we have a coffee table full of IR remote controls in the first place. Our story begins with an inventor named Philo Taylor Farnsworth. Philo worked on a device that would allow scans of lights to be electrically transmitted, and he performed the first demonstration of his device in San Francisco on September the 7th, 1927. Although his demo only sent 1 line of video, it's considered to be the first demonstration of a video transmission. Philo refined his system and performed a full demonstration of a complete picture in 1934. In 1938, Philo Taylor Farnsworth received the patent for television. After the end of the Second World War, television sales started to boom, but there was still one thing missing: the couch potato with the remote control. His day wouldn't come until the end of the 1940s, when Zenith introduced the Lazy Bones remote control, the world's first television remote. This was a wired remote control that would allow you to change volume and channels, and it cost $30, which if you translate into today's dollars is about $387, enough to buy not only the remote control but the television to go along with it. In 1955, Zenith cut the cord and introduced a visible light remote. This was an interesting device called the Flashmatic, and it worked with photocells in the corner of the television screen, which you aimed what was basically a flashlight at. Needless to say, a visible light remote had a lot of problems with false triggering. Just 1 year later, Zenith introduced the Space Command. This was an ultrasonic remote controller that used ultrasonic sound to perform functions, and this was a big hit. The ultrasonic remote controller used a series of tuning bars which were hit with a little hammer every time that you pressed a button, so the remote control didn't need batteries. This type of remote control remained popular for almost 20 years. By the end of the 1970s, infrared remotes had taken over. And by the early 1980s, there were many more devices to control than just televisions. Remote controls also controlled audio equipment and VCRs, and soon remote controls would come out to control things like lamps and air conditioners as well. As their name would imply, an infrared remote control works in the infrared spectrum of light, below the red visible spectrum. Most infrared remote controls work at a wavelength of 940 nanometers, but they can range between 850 and 960 nanometers. Remote controls send infrared pulses to the receiver. These infrared pulses are modulated with a carrier, which allows them to be distinguished from the infrared background noise. The carrier frequency can be between 30 and 60 kilohertz. The most common carrier frequency used with IR remote controls is 38 kilohertz. Now, every key that you press on a remote control transmits a unique code. Keys that are held down can also transmit repeat codes as well. This is used for things like volume controls and other adjustments. Remote control data is sent in a serial format. Remote controls use 3 different forms of data modulation and several variations of these forms as well. Pulse density modulation, or PDM, can also be referred to as space encoding or pulse distance modulation. With this scheme, the duration of the space between pulses is modulated. An example is a 0 equaling a short space and a 1 equaling a long space, as illustrated here. Pulse width modulation, or PWM, could also be called pulse encoding. In this case, the width of the pulses is modulated. In this example, a 0 is a narrow pulse and a 1 is a wide pulse. There are several forms of biphase modulation, which is also called Manchester encoding. This type of modulation modulates the transition between the high and low levels. An example is a 0 equaling a high to low transition and a 1 equaling a low to high transition. In addition to the different modulation types, there are many different protocols used with IR remote controls. Many of them are proprietary for specific manufacturers, but some are used by many manufacturers. These protocols differ by several factors, including things like error checking, the order of the bits, the number of bits, the repeat code format, and the number of stop and start bits. In this chart, you'll see a description of a number of different IR protocols. Note that this chart is by no means extensive. There are literally hundreds of these. The NEC protocol is probably the most popular protocol used with remote controls, and about 80% of consumer electronic devices use this protocol. Here's a breakdown of the NEC protocol. This 32-bit protocol starts with a 9 millisecond leading pulse burst. After that, it's followed by a 4.5 millisecond space. The next 8 bits are the address, and the 8 bits following that are a logical inverse of the address. The logical inverse is used as a form of error checking. After that are 8 bits of the command, and the 8-bit logical inverse of the command. Every packet ends with a 562.5 microsecond end-of-message pulse burst. There is also a different format for the repeat code. The key values to note when working with remote control protocols are the address and command values. This scheme allows multiple remote controls using the same protocol to exist in the same room. For example, these 2 remote controls both use the command hexadecimal 0A for an on-off signal. However, as they have different addresses, they do not interfere with one another. Here's a block diagram of the operation of an infrared remote control transmitter. When a key on the keypad is pressed, its value is sent to the encoder. The encoder determines the IR code that is necessary for this key and sends that off to a modulator, which modulates the data accordingly. This signal is sent out to a driver, which drives an infrared LED. Now here's a block diagram of the receiver side. Notice that the first three items in our block diagram are generally contained in one IR receiver module, similar to the modules we'll be using today. In operation, the IR diode in the receiver module sends its signal to an amplifier. The amplifier then sends the signal to the demodulator, which demodulates the signal, and to a decoder, which decodes what to do with the actual code it received. That action is then performed on the device that it controls. Today we'll be using microcontrollers to work with infrared remote controls. We'll be using components like an infrared LED and an infrared receiver. These are both inexpensive and easy to obtain. So let's start working with infrared remote controls. Now I've got some infrared components over here to show you, and these are the type of devices we're going to be using in today's experiments. Now these two are infrared emitters, and they both emit at the same IR frequency, 940 nanometers, but they look very different from one another. This one's in a clear case, and this little bullet-shaped one is in a dark case, which of course can pass infrared light. Now these are receivers, and these two devices are infrared receiver modules. And if you take a look at them, they're very tiny little devices, and yet they pack a lot of stuff in them. One of the things they pack in them is one of these. This is an infrared receiver diode, and the diode is the actual component you see just sticking out the front of the receiver module. The module demodulates the signal and presents a digital output, whereas the diode has a raw signal, and we normally wouldn't be using an infrared diode with our experiments, but we are going to use one right now just so I can show you the difference between an infrared receiver module and an infrared diode. And so I've got a little demonstration hooked up over here to the oscilloscope, and it's a very simple demonstration. What I've got is an infrared receiver module over here and an infrared receiver diode here. Now, an infrared receiver diode is actually the first component in the IR receiver module, but the receiver module has a number of other components in it. It's got amplifiers, automatic gain controllers, demodulators, etc. So these produce a very different output. Now this is just basically hooked up to the 5-volt power supply, and it's got a capacitor right across the power supply that's used for filtering, and we'll be doing that with all of our hookups today. And the diode itself is reverse biased, and it just has a resistor on it. And this will basically produce a voltage every time that it's hit with IR energy. It's also sensitive to visible light energy, so this blue reading, which you see on the scope, which is the diode, is actually showing a small waveform. That waveform is interference it's getting from the lights within my room. Now those are the visible lights. They're LED lights, but they do provide interference. When I turn them off, that line goes flat. And the yellow line over here is the line for the infrared receiver module. So I've got a remote control over here, a very simple one we're going to be using today, and it uses the NEC command set, and I'm going to aim it at this, and you can see we get things on both the infrared receiver module and the diode. Now the module is the yellow one, and you can see when we get it, we sometimes have a series of small pulses. I'm holding it down. This is the repeat code, whereas you can see on the diode we're getting a corresponding signal, but it's a very different signal. What we'll do is we'll capture one of those signals here on the scope and take a better look at it. So let's just give it a pulse. And there we go. We've got one captured, and now you can see both the blue, the raw diode signal, and the yellow one over here, which is the IR receiver module. Let's just take a look at the receiver module by itself at first, and what we'll do is we will make it a little bigger. And if you remember the diagram I had of the NEC protocol, we can actually see it at work. This is the start bit over here, and this bit at the front over here, if I expand it a bit, this is the address. This is the address of all zeros, which is first of all sent as all zeros, and then sent as the inverse, which is all ones. And if you recall, it does that as an error detection technique. And then after that would come the data. And so if we go down through it, excuse me, I meant to do this. We'll move down through the data, we see the end of it, and then we see the stop bit, and then after that we see the beginning of what is the repeat pulse when I hold down the IR remote control. Now if we go to the signal we got from the diode, you can see it corresponds to the signal we have over here. Everything we have on the diode corresponds to that, but the diode signal, of course, is a lot harder to interpret. Let's just see over here if we can get the scale up so you can see it. You can see that in the signal itself, very carefully, you'll even see the 38 kilohertz modulation within it, but that signal is being converted into this other signal over here by the IR receiver module. So this clearly shows why you want to use a receiver module and not just a straight diode, but it also shows what's actually going on in the background when you use an infrared remote control. All right, now that we know a little bit more about infrared remote controls, it's time to get to work and start using them. We're going to hook a circuit up with an Arduino Uno, an IR sensor, and an IR emitter, as well as a few push buttons, and we'll perform a few experiments, starting with experiments using the Arduino IRremote Library. The IRremote Library is likely the most popular library for working with IR remote controls, and it has a lot of features and a lot of example code, and we're going to go over some of that. But before we hook up the Arduino, I want to go over the IR emitters and the IR receivers in a little bit more detail. Now, a lot of the code that we're going to be using today will be based around the very popular library for infrared remote controls, the Arduino IRremote Library. And despite its name, it can be used with other microcontrollers aside from Arduinos. Now, this is a very well-maintained library. You can see there are some commits over here as recently as 2 days ago, and it provides functions for both sending and receiving infrared remote control codes. Now, it's very, very well documented. There's a lot of documentation here. You'll have no trouble finding out information on how to use it, and the library also comes with a number of really great examples, and we're going to be running a couple of examples today. So let's get this library installed, and it's very easy to do. We'll need to move to our Arduino IDE, and we can install it right in the library manager. So open up your library manager and type in IR remote, one word. And you can see IR Remote by Sheriff. Now I've already got version 4.2 installed, but of course you can click on the install button to put this into your Arduino IDE. Once you do, it will also install all of those example files, and as soon as we wire up an Arduino and some infrared receivers and diodes to it, we can start playing with all of those examples. So let's go and do that now. We'll be basing our experiments today upon an infrared remote sensor module and an infrared emitter diode, which is like an LED that emits infrared light instead of visible light. Here's a block diagram of the internals of the infrared remote sensor. Note how it relates to the pinouts on the remote sensor module. In this block diagram, we can see that the input is an infrared LED which picks up the pulses of IR light. This goes through some input conditioning and then to an automatic gain control. After that, a bandpass filter removes the unwanted components, and a demodulator takes out the 38 kilohertz. This is all under the control of a control circuit. The output goes to a transistor, and it produces a clean digital output. There are a variety of infrared remote sensors available, including the Vishay TSOP384XX series, which operate in the 30 to 56 kHz range. There is also the Vishay TSOP344XX series, as well as the older TL1838 or VS1838B series, which operate at 38 kHz. Another popular device is the Osram SFH5110-XX series. Now, if you're wondering about the XX in the part numbers, this is how it is broken down for the TSOP384 series. If we want the 38 kHz module, which is the most popular, we would choose a TSOP38438 module. Another popular module is the Vishay TSOP324XX series. However, you should note that these modules have a different pinout. This is true of some other IR remote sensors as well. So when using your IR remote sensors, make sure you look at the spec sheet and determine the correct pinout. Now let's focus on the IR emitter diode. These devices are available in different infrared wavelengths. You also have a choice of different output power capabilities, and some of these have quite a bit of output power. A very popular series of IR emitter diodes are the OSRAM SFH45XX series of diodes. In this case, the XX determines the wavelength of the infrared diode. So if we want a common 940 nanometer diode, we would choose an SFH4544. This diode has a 100 milliamp maximum forward current, which is much higher than most visible LEDs. It's even capable of 1 amperes of forward current when it is pulsed. Another popular IR emitter diode with similar specifications is the Vishay TSAL6400. Now, as an IR emitter diode is like an LED, connecting it to a microcontroller may seem to be pretty simple. All we would need to do is connect the dropping resistor to the output pin and connect our diode's anode to that and the cathode to ground. However, this is not the optimum way of using an IR emitter diode, as they can consume a lot more current than an MCU can give on its output pin. A better method of doing that is to use a switching transistor and to provide a voltage and dropping resistor for the IR LED. The dropping resistor is optional. In some cases it's not even necessary, as the IR LED can consume all of the current that you can provide it. You could also use a higher voltage than that used by the MCU in order to get higher performance out of the IR emitter diode. In some cases, you can connect two IR emitter diodes in series to get improved performance. Now here's how we'll wire up our emitter diode and IR receiver. We will be using an Arduino Uno for these experiments. We're also going to require 3 push buttons. These are momentary contact, normally open push buttons. We're going to need a visible LED as well, and this can be any color you like. This will be called our user LED. We'll need 3 resistors, a 220 ohm resistor, which is actually the dropping resistor for the LED, a 33 ohm resistor, which is the dropping resistor for the IR LED, and a 1K resistor. Note that if you're using one of the newer series Arduino Unos, the revision 4, you'll want to increase that 220 ohm resistor up to 330 ohms. We'll also require a transistor to switch on and off our IR LED. You could use a 2N2222 or 2N3906. Note that there are other switching transistors that you could use, but you should check the pinout of those, as they may not match the pinout illustrated here. And finally, we'll require a 2.2 microfarad capacitor. This is acting as a filter capacitor for the IR receiver, so you should place it physically close to the IR receiver on your breadboard. We'll begin by connecting the 5 volts from the Arduino Uno to the VS pin on the IR receiver. We'll connect the Arduino's ground to the ground pin on the IR receiver. We'll also connect the 5 volts and the ground to the 2.2 microfarad capacitor. Make sure you get the polarity on the capacitor correct. Next, we'll connect pin 2 of the Arduino to the output of the infrared receiver module. Pin 3 of the Arduino Uno will be connected to one end of the 1K resistor. The other end of the resistor will be connected to the base of our transistor. We'll connect the emitter of the transistor to ground, and the collector of the transmitter will be connected to the cathode of the infrared LED. We'll connect the anode of the infrared LED to one side of the 33 ohm dropping resistor, and the other side of that resistor will be connected to the 5 volt line. We'll connect pin 5 of the Arduino Uno to one side of the 220 ohm dropping resistor. The other side of the 220 ohm resistor will go to the user LED's anode. The cathode of the user LED will be connected to ground. And finally, we'll connect up our push buttons. We'll connect one side of push button 3 to pin 8 on the Arduino. We'll connect push button 2 to pin 9 on the Arduino, and push button 1 will be connected to pin 10. We'll connect the other side of push button 1 to the ground, and we'll do the same thing for push buttons 2 and 3. And this completes our wiring. Now let's go and use it to experiment with infrared remote controls. So now that we have our library installed and everything's hooked up, the first example that we're going to be using is the SimpleReceiver Example. And the name of this example pretty well tells you what it does. It just receives infrared signals from the remote control and displays information about them, the code and the protocol, etc., on the serial monitor. And it's a pretty simple sketch. A lot of it is actually just remarks and documentation. There's actually very little code over here. Now we start off by defining which of the protocols we want to pick up on, and right now the only one is the NEC protocol, which, as I said earlier, is responsible for about 80% of all remote controls. If you're trying to define another protocol, you're going to have to unremark that particular protocol, and we'll take a look at that when we're running this example. Now this example comes with a second file, and you'll find this second file in many of the other examples as well. It's called Pin Definitions and More, and it also pretty well explains what it is. The key part of this file is this table over here. It shows you how to wire different microcontrollers up for the examples, and then the pins will be correct. You won't have to change anything. So right now we're using default AVR with our IR input on pin 2 and our IR output on pin 3. If you're using a different microcontroller, let's say an ESP32, it tells you which pins you can use for default, so that's good to know. Now, you have to do this decode statement very first thing in the code. It has to be done before the include of IRremote.hpp, which is how you include the library. So we've done this up over here. Now we include the Arduino library, we include the pin definitions and more we just looked at, and then we include the IR remote. Now in setup, we're going to set up our serial monitor. He does a print over here just to tell him the current file date and what he's running on the Arduino. That's not really important to the function of the IR. This is important to the function of the IR. We do an IR receiver begin, and we specify the receive pin, and this enable LED feedback. If this is in there, it means that the built-in LED on the Arduino, the one connected to pin 13, is going to flash every time we receive an IR code. So you can put this on to get some visual indication. Then we just print the serial monitor, and we're ready to go. Now in the loop, all we're doing is checking to see if we've actually received something and we've decoded it, and if we have, we print out a short summary of that using some of the built-in functions of the library. If it's bad data, we print out receive noise or unknown. And down over here, a very important thing is that we have to resume after doing this, because after capturing IR data, we need to resume to start looking for more IR data. Over here, they also give you an example of what you can do if you capture a specific command code. So if you happen to know the code for 10 or 11 hexadecimal, you can do something, but it's actually not really being used in this sketch. So it's actually a pretty simple sketch. Again, there's more documentation in it than actual code, which is great. It helps you understand how it works. We'll just load this up to our Arduino and beam some remotes at it and see what happens. Okay, now to test my SimpleReceiver, I've got a few different remote controls, and I've got my serial monitor open as well. So let's just take this television remote, and we get a reading. It says it's an NEC protocol. It gives an address and a command, as well as the repeat values. And if I hit another key, you'll see the address stays the same, but the command is different for every single key. So that seems to work. And I've got this little remote that you're going to be seeing quite a bit of today in our testing. I'm going to try this one out. And it also gives me an NEC command set. It gives me an address of 0, and as I press the different buttons on it, we can see that the command changes and the address is the same. Now, if I take this remote over here, this is a Sony remote, and I press it, I get protocol unknown, and I get a lot of information about the raw data. And the same thing is going to happen, I believe, if I hit this one here. I'm going to get protocol unknown. Now this is a Panasonic remote, and this is a Sony remote. And we can go back in the code and see the reason for that. Let's just drop the serial monitor for a moment. We've only defined to decode the NEC and nothing else. So let's define the Panasonic, because we had a Panasonic one. And we'll also define Sony, and that was down over here. And so we will just send that up to our Arduino. We're done uploading, and we can put the serial monitor back on if we wish. There we go. Okay, now let's take a look and see if we can decode our Panasonic. And there it is, protocol Panasonic. It gives you the address and the command, and it's working fine for that. And the Sony. And now it's giving me the Sony values as well. And so in order to decode a specific brand of remote, if it's not the NEC, you're going to have to unremark it in there. The NEC is responsible for about 80% of all remote controls, and it still works just fine here. And so you'll find most of your remotes will use that. But if they don't work, just go and take a look at the brand you're using and unremark it. And the SimpleReceiver will tell you what it is you've got and what the control codes are. So now that we've seen how we can receive IR data, let's take a look at a sketch that can send it. And this is the SimpleSender. Now, this sketch is another example that you'll find included with the IRRemote library. And as with the last sketch, most of it is comments. There's actually very little code that you need to send data. What this sketch is going to do is it's going to send NEC command codes, but it's going to continually change them. It's going to step up through them. So if you happen to have any IR devices in the room that respond to NEC command codes, they may start to respond to this at some random time, so you've been warned. Okay, so we're going to start off by including the Arduino library, and then we do this definition, disable code for receiver. We can do this if we are not going to be receiving data and only sending it, and it'll save us some memory in our Arduino by doing that. Now we're going to include pin definitions and more, and you'll notice that file's up here as well. That's the same file we saw before that just defines the pinouts for all the different microcontrollers. And of course we need to include the IRRemote library itself. Now we'll go into setup, and you'll notice we're going to set the LED built-in to an output. That may seem a little strange because we're actually not using it in this circuit and we never call it anywhere else in the code. But the reason for that is that the library, when it sends, has an option to blink that LED on and off with a send so you can see what's happening, because obviously you can't see the infrared light. And if you enable that, you're going to need to have that set up as an output, so they do that. We'll set up our serial monitor. And this is the same thing we saw before. It just basically prints out the file date and everything, and the IR pin that we're going to. Now here's the actual action here, the IR sender begin, and you'll notice we give it a disable LED feedback. If you set it to enable LED feedback, you would see the built-in LED on pin 13 flash every time we sent out IR signals. Now these commands, which I'm surprised weren't at the top, are the numbers that we're going to be seeding the IR signals that we're sending out, the initial command and the number of repeats, and those are going to be changing throughout, so we're going to send out different commands and repeats with this. And that's what we're going to do in the loop. We're going to start the loop by printing out the current send values, the address, and the command. And then we're going to print out that we're sending a standard 8-bit address, yes. Here we go now. We're doing the IR sender. We're going to do send NEC, which is how you send an NEC code. And here we go. It's the address, the command, and the number of repeats. So address is going to stay at 00. The command is going to be variable, and the number of repeats is going to be variable as well. And here's where we change the command, the number of repeats. We can go up to 4 different repeats. We'll put a 1-second delay at the end of this, and then go and do it over and over again. So again, it's a pretty simple sketch. A lot of it is just comments and printing. The actual command is just down over here, IR sender. And so let's just load it up and see if it works. So I thought the easiest way to test the SimpleSender was to use the SimpleReceiver along with it. So I've taken a second Arduino and I've just got the receiver module as well as the capacitor that we're using to clean up the power on the receiver module. And it's picking everything up, and I've got both of the IDEs running on the screen right now. So on the left you will see the SimpleSender, and on the right you'll see the receiver, and you will notice that the sender sends out a command and it repeats it 4 times. And on the receiver side you can see it's receiving both the original command and 4 repeats. So that's why there's 5 actions for everything that's sent out. So if you look at the bottom line right now where it's sending command hexadecimal 38, for example, you will see that on the right side along with the 4 repeats on it. So it does seem to work pretty well. Now what the sender is doing is it's incrementing the command, but it's also going to increment the address. So these two can just sit here all day and send out all the various NEC addresses and commands. And so if you have any devices in the room with it, eventually some of them may start responding to it. So just a bit of a warning on that. But this is a really easy way to see how you can both send and receive infrared signals with an Arduino. So far we've been using examples from the IRRemote library, but there are other libraries out there as well for working with infrared remote controls. And we're going to look at another one right now, the IRMP library. The IRMP library is very similar to the IRRemote library. In fact, a lot of the sample code that comes with it are the same examples that come with IRRemote, so you can see how the different code changes between the two libraries. However, this library can understand about 3 times as many IR protocols as the IRRemote library can. So it does have an advantage in that respect. Now what we're going to do is we're going to hook up sort of a classic example. It's called the AllProtocols example. With AllProtocols, you hook a liquid crystal display, yes, an old school 1602 LCD, up to your Arduino, and you can use this sketch in order to interpret the command and address codes for virtually any remote control. So let's go and take a look at how we hook up our liquid crystal display, and then we'll use the IRMP library and the AllProtocols sketch to build a really useful test instrument. The IRMP library is a functional equivalent in many respects of the IRReceive library. It handles both the sending and receiving of infrared signals, and it's used in pretty much the same way. Like the other library, it has a lot of documentation up on GitHub, so you should have no problem getting it to work for you. It also contains a number of different code examples, many of them you'll notice being the exact same examples as used with the IRReceive library. Now, installing this library is as simple as installing IRReceive because we can do it right within our Arduino IDE. So once again, we'll go into our library manager and we'll type IRMP. And there it is. Now I've got version 3.6.3 installed, but you of course will want to install that, which will also install the example files. Once you have that installed, we can start using this library. The 1602 LCD display is a popular display, and it derives its name from the fact that it has 2 lines of 16 characters. You can also use a 1604, which is a 4-line display for this experiment if you don't have a 1602. This display has an LED backlight, and it's available in different colors. There's an external contrast adjustment that you need to apply to the display in order to improve its performance and readability. This display has a parallel interface, and it can be used in either 4-bit or 8-bit mode. There is also an adapter available for this display that will allow it to be used in I2C mode. However, we are not using that in this experiment. All of the connections to the display are along the top, and they are as follows. The first pin is a ground pin. On some displays, this may be labeled as VSS. The second pin is the VCC, or power pin. Most of these displays are powered by 5 volts, but there are 3.3 volt versions available. On some displays, this is labeled VDD instead of VCC. VO is the input for the contrast control. You'll apply a control that can range from 0 to VCC in order to adjust the contrast. The RS pin is the select line, And interestingly enough, the display has a read-write line. This is pretty interesting because the display never actually writes anything and should always be kept in read mode. You can do that by grounding this pin. There's also an enable pin to enable the display, and 8 pins for the parallel data output. When used in 4-bit mode, pins D4, D5, D6, and D7 are used. And finally, there are connections for the backlight LED, the LED's anode, and the LED cathode. We'll be using our 1602 display with an Arduino Uno. We'll also need a 10K trim pot. This will be our contrast adjustment. We'll require a 220 ohm resistor, and this will be the resistor for the LED backlight. Note that some models of displays already have the resistor internally, but if you're not sure, it's best to use it. If you're using one of the newer Arduino Uno R4s, you'll want to increase this to 330 ohms to reduce the current consumed. We'll need a 2.2 microfarad electrolytic capacitor, and our infrared sensor. This can be a TSOP38438, a TSOP34438, or a TL1838. We'll begin by connecting the 5 volts from the Arduino to the VS on the IR sensor. We'll connect the Arduino's ground to the sensor's ground. We'll also connect the power supply to the electrolytic capacitor, which should be situated near the IR sensor. Note the polarity on the capacitor when you're connecting it. We'll connect pin 2 of the Arduino to the output of the infrared sensor. Now we'll hook up the LCD. We'll connect the Arduino's ground to the LCD ground, and the 5 volts to the VCC or VDD pin on the 1602. We'll connect pin 7 of the Arduino to the RS pin on the LCD. Pin 8 of the Arduino will go to the EN or enable pin on the LCD. Pin 3 will go to data pin D4. Arduino pin 4 will go to LCD pin D5. Arduino pin 5 will go to LCD pin D6. And Arduino pin 6 will go to LCD pin D7. We'll connect 5 volts to one side of the contrast potentiometer. We'll connect ground to the other side of the pot, and we'll connect the pot's wiper to the VO pin on the LCD display. We'll also connect 5 volts to one side of the 220 ohm dropping resistor. The other side of the dropping resistor will go to the anode connection for the backlight on the display. And the cathode connection from the LED will be connected to ground. It's also a good idea to ground the RW pin on the 1602 display. And this completes our wiring. Now let's take a look at the code that we're going to be using with our infrared sensor and LCD display. Now, in order to test out the IRMP library, we're going to be using the AllProtocols example. This is the example that prints out the results using every single possible protocol. So coupled up with the LCD, it actually makes a pretty handy tool for testing out IR remotes. Now, there is so much code over here, I'm not going to go through all of it. A lot of it is exceptions for using different types of displays, and I do want to show you that because you can use a different display if you want to. If you get down around line 60, you'll start seeing where you have some different options. You can define it to not use a display at all and just use the serial monitor, but really what's the fun in that? You can also unremark this to use a serial LCD, and that would be the LCD display with the I2C adapter. You can use that, however, apparently by using that you will be missing out on some of the repeat codes, so that's why I wired it in parallel function. You can also, if you wish to use a 2004 display, a 4 lines of 20 character display, you can unremark this over here. But otherwise, a lot of the code over here is a lot of ifs and ends ifs for different cases, but essentially what it's doing is it's picking up on the IR codes, and it's going to produce the information on the liquid crystal display as to what the command code is and what the protocol is. So let's just load this up and see if it works. Okay, let's test out our AllProtocols display device. Now you can see I've booted it up, and hopefully you could read the display. It says IRMP All, and it gives the version 3.6.3, and then the date, and that was the date that I actually compiled it. It's not today's date. Now, what we have to do is just basically aim a remote at it. So I've got this one here, and it tells me it's an NEC, and it gives me the address, and it also gives me the control data, the command data, excuse me, and the R means it sees a repeat on that. And so it pretty well sees a repeat on everything I press, because it just takes a little press to make repeats. So you can see that it gives me all the command codes. Now, I'll take this other one over here, the TV remote that I had. You'll see the address has changed. We noted that earlier when we used this remote. And again, I've got all the command codes over here. Now let's try the Sony one, because of course the Sony one gave us problems initially in the old one, but it's fine. SIRCS is the Sony infrared control protocol, and it gives me all the different values I need for that. And we can do it over here as well with the Panasonic, and it tells me it's a Panasonic and gives me the values. So it really is capable of decoding just about everything I've thrown at it. I thought one neat thing to do is that over here I've got our SimpleSender example. So let's just power that up. And there we go, and we can start seeing all those NEC protocols as they are stepped through with the SimpleSender being picked up over here on the AllProtocol receiver. So this is really a handy dandy little device. One thing I didn't demo to you is over here we've got the pot for the contrast, and that lets you just set the display the way that you want it. Oops, I got it down too much. There we go. And so there you go. It's actually a pretty handy little instrument to have around if you're working with remote controls. And I think it's worth all the extra effort to do all the parallel connections to the LCD display to have a device like this. Now, in the IR video I did 5 years ago, I actually managed to somehow get a television onto my workbench in order to perform a number of experiments. I'm not going to do that today. I don't think the workbench could accommodate a television anymore because it has a lot more things on it. So instead, I'm going to use this. This is an infrared remote controlled lamp. It's a very simple device. The control just basically has a power switch on it, plus switches for adjusting the intensity level of the lamp. It's also got some timer switches, but we're going to ignore this. What we're going to do is we're going to take the circuit that we've already hooked up, and we're going to convert it into both this lamp and into the remote control. In other words, we're going to emulate both of these in code. And by doing this, we're going to have built a complete infrared remote control system, and you can use this as a prototype for building your own infrared remote control stuff. So let's start off by building the equivalent of the lamp, the infrared receiver, using our Arduino Uno. Now here's the sketch that we're going to be using on the receiver side. In other words, we're going to be emulating the lamp that's being controlled by the 3-button remote. And it's a fairly simple sketch. Now you'll notice it's just one file by itself. I don't have a separate file with pin definitions. We'll be performing those in the sketch, and you can use this as an example, of course, for your own sketches. Now we're going to specify the protocol we're using, and I'm using NEC protocol because that's what my remote uses. Of course, you'll have to change this if the remote that you're using uses a different protocol, but this is the most popular one. We'll include the required libraries. That would be the Arduino library and the IRRemote library. We'll define the pin that the IR receive is on, and that's on pin 2. We'll also define a pin for our LED, and that's the visible LED on pin 5. Then we define a number of variables that we're going to manipulate within the callback that'll be called every time that we receive data. So we've got this Boolean for the data being received, a Boolean that is the lamp power. If it's true, the lamp is on. If it's false, the lamp is off. And an integer for the lamp level. And notice they're all volatile because they're being manipulated within the callback. We define the codes that are on our remote control that we're interested in decoding. And so my power code is hexadecimal 0A, my minus code is 09, and my plus code is 0B. Now, of course, with your remote control, you will probably have different values, so you need to change these ones accordingly. Then there's the receive callback function itself, and this is really where most of the work is done. This is called up every single time that we receive data. We decode the data, and then we see if it matches one of our codes, one of the 3 codes up over here. So if it matches the power code, we're just going to toggle the value of that Boolean that represents power. So if it's on, we'll turn it off. If it's off, we'll turn it on, etc. If it is the minus code, then what we're going to do is we're going to change the value of the lamp level. However, we're only going to do it if the lamp is on. If the lamp's off, we're going to ignore this. So if the lamp is on, then we're going to reduce the lamp level by 16. We aren't going to let it go below 8. We could change that to a 0 and get it to be all the way down to off, but I thought that that was confusing with the lamp being off. So I set this value to 8. If it drops below 8, we're going to set it to 8. We won't let it go any lower than that. And in a similar fashion, this is the code for the plus button. This will increase the level on the lamp. So as long as the lamp is powered on, we'll add 16, and we'll make sure we don't exceed 255, which is the maximum value we can give the PWM controlling the lamp. Then we'll set the data receive flag to being true and resume receiving. So you'll notice we didn't actually manipulate the lamp directly in the callback. A callback is like an interrupt service routine. You only want to do a few basic things in it. Now in the setup, we're going to set up our serial monitor. We'll define our LED as being an output, and we'll set that LED off to start with. And then we'll start the IR receiver, and we're going to enable the LED feedback so that we'll get a flickering on the built-in LED every time we receive data. Now here's where we attach our callback handler. So we'll attach that callback handler we wrote, and we can go into the loop. In the loop, we check to see if there is IR data received, and that's that Boolean that we set in the callback. So if that happens to be true, we know we've got new data. We'll print the power and the level out to the serial monitor, and then we'll set the lamp up for that. Now, if the lamp is turned on, then we know we just use an analog write to give it the level, and that'll set the brightness on the lamp. Or if the lamp is off, then we're just going to set it to off. We're going to turn off the LED. Then we have to make sure to set our flag back to false so that it'll trigger the next time, and we do the loop over again. So it's actually a pretty simple sketch when you break it down into its components. Let's load it up and see if we can control our LED using our remote control. And here's a demonstration of our dimmable LED. Now this is my LED over here, and I chose to use a white LED because after all, the original device does have a white LED. So I've got my remote, and I can turn the LED on and off, and you can see on the serial monitor I'm getting the power and the level of the LED. I can reduce the brightness of the LED if I wish. And you can see that my level is going down, and it drops down to 8, and it won't go below 8, and that's because of the choice I made in the program. You can get it to go down to 0 if you want. I just thought that was a bit weird because it looked like it was off. I can also hit the plus button, of course, in order to increase the level. And here, I'll bring it down to a level. It's at a level of a 95 right now, and I'll turn it off. And I'll turn it back on, and it comes back on at a level of 95. And when it's off, hitting the minus and the plus, even though it's giving me an entry on the serial monitor, isn't doing anything to the readings because it's, after all, off. And so we'll turn it back on, and I can continue to use it. So it seems to work perfectly. So we've used an Arduino to emulate a dimmable lamp and used its original remote controller to control it. Now here's the code that we're going to be using to emulate our remote control sender. And we're going to be making use of the TinySender library this time. The TinySender library is packaged with the Arduino IRremote Library. And as its name implies, it's a very tiny library. It's very lightweight. It doesn't use up much memory. Its disadvantage is it doesn't understand as many different protocols. But if you're just using NEC protocol, it is actually a good library library to use because it can save some space in the memory of your Arduino. And so we're going to include the libraries we need, the Arduino library and the tiny IR sender library as well. We'll define the pin that our LED is on, our transmitter LED on pin 3. We'll also define the pin for our 3 different buttons. Now we'll define the code variables for each of the buttons. Now on my remote, this will obviously change for your remote control, but the power button on mine sends a hexadecimal A, the minus button is a 9, and a plus button is a B. And of course, if your remote is different, you would change these values accordingly. And then we're going to hold the variables that we need to send a complete IR message. We need the address, the command, and the number of repeats. So the address is always going to be 00 for my remote, and again, for your remote, it may be something different. The command is what's going to change, but we're going to set it to default to the power right now, which is a 0A, and the number of repeats is 0. Now this is a flag we're going to be using, and it's a boolean just to say that a button has been pressed. We'll initialize it as being false because a button hasn't been pressed. Notice that the command and the boolean are volatile. That's because we're going to be manipulating them in an interrupt service routine, which is the next thing that we look at actually. This is the pin change service routine. Now with pin change interrupts, you don't get an interrupt on a per pin basis, you get it on a group. So this is group B. Group B pins on the Arduino Uno go from pin 8 to pin 13. So anytime there's a change on one of those, you'll fire off an interrupt. Now, this is the interrupt service routine that's going to get fired off every time the interrupt occurs. And like any other interrupt service routine, you want to do stuff that's as quick as possible and just get out of there. So the first thing we're going to do is see to make sure button pressed is still false. If it's not false, then this might be a false trigger, because don't forget, when we press one of these buttons, we'll probably fire several interrupts up because of all the noise in the button and everything. So as long as the button has indeed not been pressed before, we'll run through this and we'll see which button it is, because we don't know right now which button it was. We only know it was one of the groups. So we'll look at each one of them, D10, D9, and D8, and for whatever button it is, we'll set the command to the particular variable that goes with that button. So the power code, the minus code, or the plus code, etc. And then at the end of all that, we'll set button press to true. Okay, so now we'll go into the setup. We'll set the serial monitor. We're just using that to test things. We'll put all the buttons with input pull-ups, and we'll also set the built-in LEDs and output. That's a requirement of the library, as we've seen before. Now, the pin change interrupts, this is how we set them up. The first thing is we want to tell it we want to enable pin change interrupts for port B, and that's what we do over here. This is port B when you set this bit to a 1. And then we have to enable the pins within port B that we want to have trigger the interrupts. We want 8, 9, and 10. And so when you look at this byte here, it's exactly the way the pins are. This is 8, 9, 10. We've set them to 1. This is 11, which is set to 0, 12, set to 0, etc., etc. And so that's how you enable the pins on the pin change interrupt. So now we go into the loop, and in the loop we're going to see if the button's been pressed, and if the button was pressed, we'll fire up that interrupt and this variable will be true. So if it's been pressed, we go and we actually send the IR code. So we'll do an IR send NEC, because we're sending an NEC code, and we'll print out the pin that we're going to send to, the address, the command, which is what's going to change for the different buttons, and the repeats, which will always be 0. Then we'll print to the serial monitor what command we actually sent, and notice when we do a print, we do a hex at the end of that, and that's just so it prints in hexadecimal. If not, it'll just print in regular decimal, which is fine, but it'll make more sense in hex to us because that's how we defined it. Then we put a short little delay over here just as part of a debouncing routine, and we'll reset the button press flag to make it false, so we're ready for the next push button press. We'll add another short delay, and all of these are part of a debounce, and that turned out to be the most problematic thing in building this, was debouncing the buttons, but this seems to have done the trick. So we'll go back into the top of the loop and wait to see if a button's pressed again. So that's the code. Let's load it up and see if we can control our lamp using our Arduino. And so I'm ready to demonstrate our home-built remote control, the one I've constructed with an Arduino. And here's the remote control that it's going to be replacing. And if you put that remote control down here beside the solderless breadboard, the buttons line up. This is the power one, this is the minus button, and this is the plus button. And of course I haven't done the 3 timer buttons. I've also put the AllProtocols LCD display over here just so you can see what's happening. And we've got the serial monitor ready to go, so we're all ready to test this out. Now let's just use the original remote first just to see the operation. And of course pressing this turns it on, and as you can see from here it gives the protocol of an A, and I held it down long enough to get a repeat. And I can hit a minus over here, and that will start to dim the light. I don't know if you see that as well in the video as I'm seeing it here. And that's a code of a 9. And then when I hit the positive over here, I get the code of a B. And this should give me the A again, which powers off the light. And so now I'm going to emulate that with our circuit over here. So this is the A. And I sent a command A. You can see that in the serial monitor, and it indeed turned the light on. And this is the minus button. And so I'm sending some 9s out, and the light is dimming. And this is the maximum it dims to. And I'll hit the other button. I'm sending out a B. And the light is coming back up, and I can turn it off again by hitting that and sending out an A. So it does look indeed like we've emulated the remote control perfectly. And of course you could do that with any remote control and any number of buttons. So if you wanted to build a custom remote that just had a subset of the number of buttons on your remote control, some remote controls have a lot of buttons you'll never need, then you could do that with an Arduino or any microcontroller, and it's very easy to do. So once again, we can control IR devices with a microcontroller. Now up to this point, the method that we've been using to decode remote controls is to determine what protocol they're using and then just set our library to that protocol so we can understand all the signals. But occasionally you're going to run into a remote control that even with the IRMP library, you cannot find the protocol. What do you do with those ones? Well, with those you can actually sample the remote data, and this is a technique you can use with any protocol. By sampling the data, you're ignoring what the protocol is. You're just literally looking at the pattern of 1s and 0s that is coming from the remote control and using that to recognize that remote. And there are 2 examples already with the Arduino IRremote Library of using this technique. And so we're going to go over those examples right now. Now in the receive and send sketch, we're going to, as the sketch says, both receive and send data. The way that it works is as follows. We will be in receive mode most of the time. When we receive a new IR control signal from an IR remote control, we will store that signal. And then if you press the push button, one of the push buttons, we will resend that signal out of our own IR diode. When we're not sending the signal, we're in listen mode again. So if we hear another IR remote control signal, we will reset ourselves to match that signal, and that will be the signal we send every time we push the button. So this is basically a trainable push button. So we're going to start off with the Arduino library and the pins and definitions file that we've used previously. And there is actually something we need to change because of this, and I'll get to that in a moment. Over here we have the usual bit for specifying protocols, and the only one is specified right now is the NEC protocol. You can enable another one if you wish, but you may not have to, and I'll show you that in the demonstration a little later. We also define a raw buffer, and it's defined differently depending on whether you have a Arduino Leonardo or a different processor, but we need this raw buffer in order to store the actual data that we're interpreting. And there's a number of parameters down over here, and you can play with these if you're having trouble with a specific remote control. Air conditioner remotes can be kind of problematic, so there's a signal down over here for some LG air conditioners that might be helpful if you unremark it, but you'll have to experiment with that that. We're going to leave it alone. Down here, they have a recommendation over here for your IR receiver, and it's interesting. It says that this recommendation is for the cheap VS1838s. Those are the ones you probably get at Amazon in your kit. If you're using something fancier like I am, you can adjust this value over here, but I'm going to leave it as it is right now. Then we're going to include the IRRemote library finally. Now this is a line you're going to need to change, and I'm going to tell you why. It maps the send button, the one we're going to use for sending, to something called the application pin. Well, the application pin is an interesting pin in that it can be either an input or an output in some of these examples. It's connected to pin 5 on the Arduino Uno, and that's a problem because I'm using it as an output. Several of the examples here also use it as an output, and I've got an LED on it for the experiment we did with a visible LED. So we need to change the send button pin from the application pin to something else. Now we have buttons on pins 8, 9, and 10, so any of those numbers will work. I'm going to put that on the pin 10, so it'll be PB1. Now there's another variable over here, the delay between repeats and the IR. Now this is a data structure to store the IR data that they do over here. Here's a Boolean they defined. The send button was active, and this is just a Boolean that's activated by pressing the button. And it sets up a couple of entries just to save for two functions that they list later, store code and send code. And we're going to go down and look at store code and send code right now. Now store code, as you might imagine, stores the code, so it's activated whenever we receive something, and it basically goes through a lot of, as it says, data logging over here, and it looks at what kind of code it is, whether it can understand it or not. It can also store the code into if it doesn't understand the code as well too. It can store it as well just as raw decoded data. And so it uses the raw data over here and stores it, or it stores the code as a format that it understands. Now send code basically just takes that data structure and sends it out. It assumes it's a 38 kilohertz signal. That's what the 38 is over here. So if you're running in the protocols that don't use that, you can play with that one as well. Okay, now we'll go back up to the setup and the loop. Now in setup, we set our button up with an input pull-up, so we didn't need a resistor. There's the same serial begin that we saw before. I'm sorry, I slipped over here with that. There we are, the same serial begin we saw before, and then he defines which AVR we're using, and he prints out the date, etc. on his serial monitor. Down over here is the next one that really matters, the IR receiver begin. We're going to start the IR receiver, enable the LED feedback, so we're going to see the onboard LED flash anytime that we get a signal coming in. And we're also going to do an IR sender. This is the other key part of the setup you need to know about. We're going to set both the receiver and the sender at the same time. Now in the loop, we're going to take a look for the push button, and we'll set its value to a Boolean. If the Boolean's actually been active, then we know the push button's been pressed, and we're going to stop receiving and we're going to send data. And so we're going to go and send the active data that we have. If the button has just been released, we're going to start receiving. And there's another situation down here too. If we are just receiving something and decoding something, we need to store it and then resume receiving. And notice that we need to restart the receiver and resume it every time, because that is turned off when we're working on the send section. And there's a little bit of a delay, and then that's it. So it's a lot of code, but actually if you read all the comments, it's quite understandable and you could reuse it for your own purposes. So let's go and load it up and take a look at it in action. So let's test out the receive and send sketch. Now here's what I've got. The lamp, of course, that I've been controlling for most of our sketches is here, as well as its remote control. I've got the display so we can display the protocol as we're sending it from either the remote or from the experiment, which is over here. And the first push button is the push button that we'll be using, so it's the white push button. I've also got the serial monitor up, and you can see that it says it's ready to receive IR signals, and it says it can do the NEC protocol the Onkyo and Apple protocol, and it'll also be ready to send them out on pin 3 at the push of the button on pin 10, which is the white one over here. So let's start off with the protocol we know it knows about. That's the NEC one, and we'll hit the NEC protocol. And there you go, we got it. Actually, we got it twice because I hit it twice. The lamp is not the most responsive thing. And it says it received address AA command 0A, and that's indeed what we're displaying on the display here. So let's just clear this display so that we can get it again and see what happens when we press this. And our lamp went off. We got a 0A, and it said now sending the protocol, and it sent it. And I can continue to send it, so I can turn the lamp back on by sending it again. Now let's give it a different protocol. Let's just clear this. And let's clear the serial monitor to make it a bit easier to read. Okay, let's give it the plus, make the lamp a bit brighter. And now it says it's a B. And you can see over here it says it received a B as well. It's ignoring repeats, it says. And so now let's clear the display here again. And we'll press the button. And we're making the lamp brighter because we're sending out a B, as it says over here on the display. And now we're trained for that, but then I can train it back to be the power button again if I wish. And now we're the power button. So it trains itself on the last thing that it received. Now what's going to happen when it gets this Sony? Because you remember we didn't enable that protocol. So let's just clear the display over here. Let's also clear our serial monitor. And we're all clear. We'll just hit the up button on the Sony remote control. And this displays it to CIRCs, which is the Sony infrared protocol. But over here you see it says received an unknown code, and it stored 31 timing entries as raw data, and it goes on to show you what it has stored and also a checksum of everything. And so that's great. So what's going to happen? Let's just reset this. Now what's going to happen when I press the button? Let's also clear our serial monitor. And we sent out the Sony protocol, and it says over here now sending raw 31 marks or spaces. So if it doesn't understand the protocol, it converts it into raw marks and spaces and sends it out that way. And in most cases, that will perfectly emulate it. So it doesn't necessarily need to be trained on the specific protocol if it's a non-NEC remote. So it's a pretty handy circuit, and you can see it's also the basis for a learning remote control. However, there is another way of doing this as well, one that's even a bit better. I'm going to show you that right now. Now the next example sketch that we're going to be using is called the ReceiveAndSendDistanceWidth example, and it does exactly the same thing as the last sketch, but it uses a different method. It uses something called the distance width protocol, which measures the width of the pulses coming in, and as it says here, it covers a lot of known and unknown IR protocols. So this is good for some of those IR controls that you just can't decode anywhere. Now it starts off basically the same as the last one. We're going to include the pin definitions and more file, which of course has our pin definitions and a bunch of constants. Then we have the IR send pin, that's the pin that we're sending out on, which is pin 3. And this is important. We need to define the mode that we're in, which is decode distance width. And this has to come before you call the IR remote. So it's important to put that up at the top of your sketch. Over here we define a buffer, and the buffer is dependent upon the amount of RAM you have, and it gets all of that information from the pin definitions file, because the amount of RAM is dependent upon which processor you're using. Now there's a number of optional things we can enable over here, and they're all defined here if you want to read them, but we'll just leave them alone for now, and we call the IR remote over here. Now where it says send button pin, we need to do the same thing we did to the last sketch. We need to change this to one of the pins that we're using for a push button. I'm going to use number 10. You could also use 9 or 8. And we have another definition for delay between repeats in milliseconds. Now this is actually the part that you really need to look at. These three items are what it is that we are storing for every pulse that comes in. We're storing an array with the raw data in it, we're storing the timing information, and we're storing the number of bits. And so that's recorded for everything that we get. We don't bother to decode protocol, we just store this. And it's pre-populated with a bunch of NEC data. We also have a Boolean that we defined earlier, and that's just for the status of the push button. And so we go into our setup, we go into the pin mode for the push button, of course, and here we just set up the serial again. And here is where we start the IR receiver, and down over here the IR sender. Everything else is just basically printing to the serial monitor. Then we go into the loop, and then we take a look to see if the push button has actually been pressed, and if it's pressed, then we know we need to stop receiving and start sending something. So we print some things to the serial monitor, and then this is where we actually send, and we use this send pulse distance width from array, and you can see the parameters of that over here. It's got quite a few of them, and so that's actually all this code over here, and that's where we send the data from the three elements that I showed you earlier. And then over here, if it was active, the button was just released, we'll activate the receiving, so we'll start the receiver again. And here's the decode section, and this is where we decode the three different elements that we need. So here's the timing information, here's the number of bits, and here's the actual raw data array decoded. And after we do that, we resume the receiver, a short delay at the end for everything, and we go back and do the whole loop again. And so let's load this up now and see how it operates. And now we'll repeat the experiment, this time with the receive and send distance width sketch. So the setup here is identical to what it was before, and I'm going to give it the NEC remote control. And I did it twice again because my lamp wasn't very responsive, but in both times it told me the same thing, that it received a pulse distance protocol with this raw data, and it gives me some information here about that data. And so that's what it's stored now for the button. So let's just reset this and press the button. And it turned the light off, and we got a 0A protocol. And on the serial monitor, it says sending 32 bits. It tells you what the 32 bits are. And it's sending it from this array with this timing over here. So it's captured the bits and the timing between the bits, which is great. Now let's just reset this and try it all with the Sony protocol. And again, it picked up some Sony stuff. It said the timing didn't change. It was the same timing as the previous one. Let's just clear this and clear this. And we can play back the Sony protocol as well. So the significant thing is that this wasn't trained on any protocols. It's just getting the individual bits and the timing between the bits and capturing it. So this can be very useful for some remote controls that just simply won't work with any of the other libraries. And it's a great way of interpreting remote control stuff as well. You could even store this data and use it again later, as I said, for a learning remote control or for some sequence that you want to automate. So it's a super technique for using for decoding IR remote controls. Now, as I mentioned at the beginning of the video, this video was going very, very long, and I had to cut out a number of projects that I'd built with the IR remote, and they were pretty cool projects too, so I want to present them in another video. However, I had to leave at least one of them in. You've come this far, you need a project, you deserve that. And so what we're going to do is we're going to take an ESP32 and use it to build an IR remote control. In fact, we're going to emulate the same remote control that I emulated earlier. The difference with this design is that the ESP32 is going to use a web-based interface, and so we can use a tablet or a phone as our remote control, and because it's a web-based interface, we can put as many buttons on it as our heart desires. And so let's go and take a look at the hookup of this. It's a very simple hookup, but I'm using a different method of driving the infrared emitter LED. Now with the Arduino Uno, we used an NPN transistor to drive the infrared emitter diode, and you could use the same scheme with the ESP32. As the ESP32 is a 3.3 volt microcontroller, you might want to reduce the value of the base resistor to 680 ohms from its original 1K value, but otherwise you would wire it identically. You would still use a 5 volt VCC for the IR diode. Another way of doing this, however, is to use an N-channel field effect transistor. This has a number of advantages over a bipolar transistor in terms of efficiency. With a field effect transistor, the gate is connected directly to the GPIO pin. I'm going to be using a TN0702 field effect transistor in this design, but you could still use the 2N2222 bipolar if you wished. If you do use the FET, the pinout is illustrated here. We're also going to be using an ESP32, and you can use any ESP32 module that you wish. We'll need an infrared LED, the same LED that we used in our previous experiments will work just fine. And we'll need a dropping resistor for that LED, and I'm using a 33 ohm resistor. We'll begin by connecting a ground connection from the ESP32 to the source pin on the TN0702. We'll connect the drain of the TN0702 to the cathode of the IR LED. The anode of the IR LED will be connected to one end of the dropping resistor, and the other end of the dropping resistor will be connected to a 5 volt output on the ESP32. Finally, we'll connect GPIO pin 4 to the gate of the field effect transistor. And this completes our wiring. And so here's the code that we're going to be using for our ESP32-based infrared remote control unit, and it's going to require a few libraries that you won't find in the Arduino IDE library manager. You'll need to go to GitHub for them, and there's two of them, the ESP Async Web Server and the Async TCP library, and these are both to run the web server in asynchronous mode. We can take a quick look at those libraries. Here is the ESP Async Web Server library, so just go to the page on GitHub and go to code and do download zip. And you also need to do that for the second library, which is this one here, the Async TCP. Now these are both older libraries, but they still work very well, and they'll work with both versions of the Arduino IDE. Once you have them, you'll need to use the install from zip function within your IDE to install them. Okay, so assuming you've got your libraries installed, we can get going with the code. We'll include all of those libraries, and we're going to be using the tiny IR sender again, the same one that we used to build the 3-button remote control, because it's very easy to work with. Otherwise, the Arduino library, the Wi-Fi library, which of course we're going to require, and the two libraries that we just installed. Now we're going to set up a Wi-Fi access point, so we need to give it a name, and we can give it a password if we like. And so I've called mine ESP32 remote. You can of course rename that, and a password should be at least 8 characters, and that is definitely 8 characters. Now if you don't wish to use a password, just put a null character in here instead. Now if you've used the ESP32 with a Wi-Fi, you'll know we usually call the Wi-Fi web server and create a server object with it. In this case we call the async web server, and this will allow us to communicate in the background, so to speak. We don't need to refresh URLs or communicate on that line, so the status of our buttons can be communicated to the server in the background without refreshing web pages, which is the desired operation. Now under here we're going to define the pin that we're using for the infrared LED, and here are the 3 codes that I'm using. Now of course if you're going to build your own, you'll put the codes you want, and you can put more buttons on, so you'll need a variable for each one of the correct codes. We're going to assume the address is always the same, and here's the variables to hold that. Now my address is 00, but if on your remote control you have a different address, then just change that. The address should be the same for all of your buttons. This is the S command, which is going to hold this value, and we initialize it with a value of 0, and this is for the number of repeats that we're going to send. We'll also initialize that for a number 0. Note that we make this one volatile because we're going to be be working with this during the asynchronous communications. Now, here's a flag that we're going to use just to let us know that a button has been pressed, so we have to leap into action. Now, under here, we use a character variable called index.html, and this is actually the entire HTML for the web page. So it's very easy to edit the HTML, and you can certainly make a much prettier page with much better style sheets than what I did over here. But as you see under here, we start off with a style sheet, and again, feel free to change some of these values if you wish. And the style sheet also covers what happens with a hover on the button and when it's active, etc. And then down over here is the body of the text, and it's very simple. And yes, I'm using paragraphs to format. I know that's terrible. I should be using style sheets, but it was the fastest way to do it. So as I said, you can make a much nicer page. But what's important is that you understand how this works. Now, I've got 3 buttons on the page, and on each button, I'm going to define what it's going to do. But before I do, I'll show you this. This is the key over here, the toggle checkbox function, and this is what does the asynchronous communications in the background. And so on a mouse down, for example, on the first button, we're going to call this function, and we pass one parameter to it, and that parameter is going to be what's on the get line in the background. So it's different for every button. For this one on the mouse down, we're going to do P on, and this is the power button. The one below it is the up button, so we do U on. The one below it is the down button. We do a D on. And there's 2 events we have to cover for each one: the toggle checkbox, the on mouse down event, and the on touch start event, because we got to look for both web pages where people are using mice, and also for screens on tablets and phones where they're going to touch them. So you duplicate this for both events, and then you also have another set of events for on mouse up and on touch end. And on this one, I'm sending P off, U off, D off, and I'm doing the same thing over here for the on touch end as well. And so if you want to add more buttons, just continue this pattern. Now we'll end the HTML and go into our setup. In the setup, we'll start the serial monitor, and then we set up our Wi-Fi as an access point. We're going to print the IP address out to the serial monitor so we can see what it is. And this is how we send the web page to the client. We're going to turn the server on and send the start of the web page over here. And then under this, we have 2 different events that happen for each button. Now, when the button is pressed, this first one's for the power button, we're going to get the P on when we get this. Then we'll set S command to the power code because we've pressed the power button. And we'll also set the button down flag to a true, and then we'll finish the HTML over here. And then when the button is released, we'll get this, and we'll again print to the serial monitor. We'll set our command to 0, 0. That means we have no command, and we'll set button down to false. And so there's 2 events for the power button. There's 2 for every button. There's 2 for the up button, 2 for the down button. So again, if you want to add extra buttons, you just create 2 of these events, and these all go in the setup. This sets up the asynchronous web server in the setup, and then after that we start the server. And then finally we jump into the loop. In the loop, we make sure that the command isn't 0, because if it is, it's not valid. We see if the button has been pressed down, and if it is, we've already got the value for the address, the command, and the repeat. So we're just going to basically send it, and I'm sending NEC because mine is an NEC, but of course if you have an Onkyo or something, you would change that. Then under here we'll print to the serial monitor to say what we sent, and we put in a short delay. And then we want to see if someone is holding down the button. So if the button down is still on and the command is not 0, the button is being held down. And so we're going to send it again, the command with a repeat. Now this really isn't the proper way to do it. The proper way would be to just send the repeat, but I can't find a way with this library to send just the repeat. I have to send the command and at least one repeat. So that's what I'm doing here. I'm sending a command with a repeat, and we sent it. We'll do a little delay, and then we'll go back and check. If it's still the same case, we'll go and do it over and over and send our repeats. And so that's the code. Let's go and load that up and see if we can control our lamp using our ESP32. And we're ready to demonstrate our ESP32 based remote control. Now let me just show you how I've got my screen set up. Down over here you can see the serial monitor, and I've just restarted the microcontroller, and it tells me my access point IP address is 192.168.4.1. Of course I've got to connect to that access point, so as you can see I've done that already. If you look here, I'm on ESP32 remote, and I've gone to 192.168.4.1, and I indeed have my web page. Now I've got my microcontroller over here and my lamp, and let's just take a quick look down at the microcontroller at the wiring. Here is the IR emitter diode, and down over here, if you can see it, the field effect transistor, and this is a dropping resistor for the diode, and you can play around with that value of dropping resistor. 33 ohms is not cast in stone. In fact, in many cases you might not need one at all, because these diodes can handle a lot of current. And here of course is the lamp we're trying to control. Let's see if we can. We'll hit the power. Give that another try. There we go. The lamp is sometimes temperamental, and as it said in the serial monitor, every time we did that we sent command A for a power, and this PWR on, PWR off is what we are showing every time we either press down or release a key. So that's just on our serial monitor, we're monitoring that. And we can also use the controls here. Let's try to reduce the brightness of our lamp, and we can send commands to go down, and we can also hold it down. So let's hold down the up button. And as you can see, we said sent command, repeat command B a number of times. Let's do the power again. We can power it off, power it on. So it does seem to work pretty well. We can do repeat commands, or our pseudo repeat commands, because you saw in the code they're not exactly perfect. And it also works to power it on and off. And of course, this is just a simple remote control, but you can use this technique to emulate pretty well any remote control. Put as many buttons as you want on it. Use your CSS and HTML skills to style everything to look really nice, and get yourself a really useful project. Now, if you want to work on some of the experiments that require an IR receiver with your ESP32, it's pretty easy to hook one up. Now, you'll need a modern IR receiver like the TSOP38438, one that can work with 3.3 volts. We'll also be using a 2.2 microfarad capacitor, and this is just for decoupling the noise on the IR receiver. For our hookup, we'll connect the 3.3 volt out from the ESP32 to the VS pin on the IR receiver. The ESP32 ground will be connected to the receiver ground, and we'll connect our 2.2 microfarad capacitor across the power supply line. Make sure you observe the correct polarity. The only other connection is from GPIO 15, and we'll connect that to the output of the IR receiver. And with this hookup, you'll be able to perform all the IR receiver experiments using an ESP32. Okay, well, I think it's about time we wrapped up this video. We've been here for over an hour and a half, and I think we've learned a little bit about infrared remote controls. But if you can't get enough of infrared remotes, I want to point out that there is an article that accompanies this video on the DroneBotWorkshop.com website. It's got all the code that we've used today, all the information that I've shown you today is in the article, plus it has links out to other resources on the internet about infrared remote controls. So if you're working with IR remotes, that's the place to go. While you're on the website, if you haven't yet, please consider signing up for my newsletter. No, it's not a sales letter. It's just my way of staying in touch with you occasionally to let you know what's going on in the workshop. And of course, it's free to sign up for. And another thing that's free to sign up for is the DroneBot Workshop forums, where you can discuss your infrared remote and other electronic projects with a bunch of like-minded electronics enthusiasts. And it's free to join the forum as well. There's information below the video about that. And finally, if you haven't subscribed to the YouTube channel, I would be very appreciative if you would. And all you need to do to subscribe is just click on that red subscribe button, and also click the bell notification. And as long as you've enabled notifications on your computer, you will get notified every time that I make a new video. So until we meet the next time, please take good care of yourself, please stay safe out there, and I will see you again very soon here in the DroneBot Workshop. Goodbye for now.